Namaskar, welcome to the channel Anka Ananda Haran, that is extracting happiness from the teaching learning process of mathematics. After a long gap, again we are coming with some new videos, but about a very known topic, that is eigenvalues and eigenvectors of chapter 5 of Gilbert-Strang book, that is Applied Linear Algebra and its Applications. Before starting the topic, let us understand what do we mean by eigenvalues and eigenvectors. We know every matrix represents a linear transformation. So, if a matrix is multiplied to a vector, that means a linear transformation is applied on that vector and that vector is transformed to a new vector. So, when we apply a linear transformation to a given vector, there are some changes that occur in the input vectors to get some new output vectors. But during this process, some vectors get rotated as well as its magnitude is changing. Some vectors only change their magnitude and some vectors change both magnitude and direction, out of which the vectors which remain as a scalar multiple of itself, that is before transformation it is x, input is x and output is lambda x, that means a scalar multiple of x. If lambda is positive, that means it is a vector parallel to x in the same direction, or if lambda is negative, then the vector is anti-parallel to x. So the vectors which are transformed to their parallel or anti-parallel vectors are called the eigenvectors or characteristic vectors, and the value which is multiplied to it is said to be an eigenvalue of the matrix A or of the linear transformation A. Let us consider a linear transformation which is given in this image. Suppose before transformation this is a vector, this is this green vector, blue vector and orange vector. Observe before transformation and after transformation, the direction of green vectors, blue vector and this orange vector remains same before and after, but whereas the white vector gets changed. So here the orange vector is negative times of itself and the other vectors direction, orientation remains same. So here before transformation, this white vector which is transformed to this image white vector, one can analyze this is some scalar times this green vector, another scalar times this blue vector and another scalar times of this orange vector. When it is transformed again, it is again some, it can be written as a linear combination of these three vectors, that is green, orange and blue. So such vectors which are eigenvectors or characteristic vectors, they can represent the output of any given input vector. So what we will do? We will write the input vectors as a linear combination of eigenvectors and we will find out the output as the corresponding multiplying the vectors by the corresponding eigenvalues. For example, here let us consider a vector V. It is an arbitrary vector, is equal to eigenvector lambda 1, eigenvector x1 plus let us consider the vector V as a linear combination of c1 x1 plus c2 x2, two eigenvectors, are there. Then what will be the image of AV? So it will be C1 times lambda 1 x1 plus C2 times lambda 2 x2. That means this image can be very comfortably evaluated. Any input vector is given, its image can be very comfortably obtained through eigenvectors. So this is one of the significant application of eigenvectors. So we got that. What do we mean by an eigenvector? Now the question is how to find out such eigenvectors of the given matrix. So first of all, before calculating, let us study the details. So here X is a non-zero vector which is transformed by this matrix A to a vector lambda times of itself, or which can be written as lambda I into X. Now this means that this equation can be written as Ax minus lambda Ix is equal to 0, or A minus lambda I whole into X is equal to 0. This is a homogeneous system. So we know homogeneous system of equation has always a solution that is a zero solution. To have a non-zero solution, that means to have more than one solution of the system of equation, this system of equation 1 should be a singular system of equation, that is the coefficient matrix of this system of equation, this coefficient matrix should be of zero determinant. That means it should satisfy this condition, determinant of A minus lambda I is equal to 0. It is one of a significant equation in eigenvalue calculation. This equation is called characteristic equation. Its roots are called characteristic roots or eigenvalues. So to find out eigenvalues of a given matrix, we are expected to evaluate the roots of this characteristic equation, determinant A minus lambda I is equal to 0. Let lambda 1, lambda 2 up to lambda n be the eigenvalues of a matrix A, which are obtained from this equation, determinant A minus lambda I is equal to 0. Then substituting lambda is equal to lambda I in the equation 2, obtaining the non-zero solutions will give us the set of vectors, non-zero vectors which satisfy A minus lambda I is equal to 0. This equation, that is, if X is an eigenvector of A minus lambda I is equal, if X is a null space vector of A minus lambda I, if X is a non-zero null space vector of A minus lambda I, then X is an eigenvector of the matrix A corresponding to the eigenvalue lambda I. So here X is an eigenvector of the matrix A corresponding to the eigenvalue lambda is equal to lambda I. So this is the method of finding eigenvalues and eigenvectors of a given matrix. Now there is a simple formula for 2 cross 2 matrices, eigenvalues, characteristic equation. What to do? Directly we can write the characteristic equation of a 2 cross 2 matrix is lambda square minus trace of A into lambda plus determinant of A is equal to 0. So here trace of A means sum of the principal diagonal elements of A. So what we will do? We will add the principal diagonal elements, that will be negated, and that is multiplied with lambda, and determinant of A is substituted here to get the characteristic equation. Its roots are the eigenvalues of a 2 cross 2 matrix. Now some of the properties of eigenvalues. So these are some of the properties of eigenvalues. What are they? A and A transpose have same eigenvalues. If lambda is an eigenvalue of A, then lambda is also an eigenvalue of A transpose. Now, if lambda is an eigenvalue of A, then lambda to the power K is an eigenvalue of A to the power K. And K lambda is an eigenvalue of Ka. If A inverse exists, That means if all the eigenvalues are non-zero, then the eigenvalues of A inverse are 1 upon lambda. Some of the eigenvalues of a given matrix are the represents the trace of the given matrix. Similarly, product of the eigenvalues of a given matrix is the determinant of the given matrix. So suppose A is an eigenvalue, A is a matrix with eigenvalue 5, 7, 9. Then trace of A is 5 plus 7 plus 9, that is 21. And determinant of A is 35 into 9, means 5 into 7 into 9. And for an orthogonal or unitary matrix A, mod of lambda is always 1. That means its absolute value should be 1. If the absolute value of a given matrix is eigenvalue of a given matrix is not 1, that means that matrix cannot be orthogonal. Okay, so here some of the properties of determinant. Suppose A is having these 3 eigenvalues. What about A square? A square will have eigenvalues, these squares. What about 5A square? That means it will be multiplied by a scalar 5. What is trace of 5A square? We will add these 3. What is determinant of 5A square? We will multiply them. What about inverse of the matrix 5A square? Then we will take the reciprocal of each one of them. Okay, so we can apply our concepts to simplify a very complicated problem. So, no, please. The eigenvalues of a symmetric matrix or Hermitian matrix are all real, and for a skew Hermitian or skew symmetric matrix are either zeros or purely imaginary. That means if somewhere in a competitive exam the eigenvalues of a matrix are 2, 2 plus 3i, 5. What about the symmetric or skew symmetric property of the given matrix? A matrix having these 3 values as eigenvalues can neither be symmetric nor be skew symmetric. Okay, similarly, we can apply this concept in a different variety of ways, but these properties are very significant, and in a very simpler way, complicated problems are sorted out. Up to this, we were discussing about the properties of eigenvalues. Now we will discuss about the properties of eigenvectors. If x is an eigenvector, suppose ax is equal to lambda x. That means, and x is not equal to 0. That means x is an eigenvector of A corresponding to the eigenvalue lambda. Now I multiply here this side again another A. So I will get here A. That implies lambda taken outside, Ax. So Ax, that is equal to again lambda into lambda x, that is lambda square x. So here it is A square x. So what we got? A square matrix is having the same eigenvector x, but the eigenvalue will be changing to lambda square. So here the property 9, the eigenvectors of eigenvectors for the ith eigenvalue, here factor 9, value of A a to the power n, ka, all are same. So here eigenvalue. So if I have taken the lambda 1, corresponding to lambda 1, if I have x1 is the eigenvector of A, then the corresponding lambda 1 squares corresponding eigenvector is the eigen lambda 1 squares eigenvector is also x. So the ith eigenvalue corresponding eigenvector are same for these matrices. Every matrix satisfies its characteristic equation. What is the meaning of it? Its meaning is, if I have a matrix with its characteristic equation lambda square minus 5 lambda plus 6 is equal to 0, then corresponding to that characteristic equation, my matrix A square minus 5A plus 6I will be always 0. So every matrix satisfies its characteristic equation. This property is also known as Cayley-Hamilton theorem. Okay, so this is one of a significant property. It simplifies the evaluation of a to the power n very comfortably. Next property is, if A is a symmetric matrix and x is its eigenvalue, then the vectors ui is equal to xi divided by norm of xi, which are called normalized eigenvectors. All such vectors will form an orthonormal sets of eigenvectors. That means if they are written as columns of a matrix, then we will be getting that matrix is an orthogonal matrix or unitary matrix. In case of real matrix, it is orthogonal, and in case of complex matrix, it is unitary, because unitary matrix, if it is real unitary, then it is orthogonal. If it is real Hermitian, it is symmetric. If it is real and skew Hermitian, it is skew symmetric. We will discuss what about Hermitian, skew Hermitian, all those things, but in the later part of the video or in the next video, according to the duration it is taking to this video. Now let us discuss some of the applications of eigenvalues and eigenvectors to real life problems, that is to solve a system of equations. Consider a vector u which is depending on t and it is having two component vectors. It is a two component vector. One component is v, another component is w. That means v is a function of t, w is a function of t. Now let du by dt is given by a into u, which is equal, and with the initial condition u of 0 is equal to u0 at the point t is equal to 0. So in this case, this is said to be an initial value problem, or it is a system of equation. Here u is the unknown which is to be obtained in terms of t, and that means the component of u, that is v and w, are to be obtained in terms of t. So to solve such an initial value problem, we are expected to take the following steps. Step 1, find the eigenvalues of a from the equation determinant of a minus lambda I is equal to 0. From this equation, we have to find out the eigenvalues of a, and from this equation we have to find out the corresponding eigenvectors of a. Then after finding the eigenvalues and eigenvectors, u of t, the general solution of the given system of equation is u of t is equal to c1 e to the power lambda 1 t x1 plus c2 e to the power lambda 2 t x2. Substitute in this equation the values the value t is equal to 0 on both sides, and substitute the initial condition u of 0 is equal to u0. to get the arbitrary constants C1 and C2. Once C1 and C2 are obtained, substitute there in the equation to get the general solution. To get the solution of the initial value problem, from where we can find out the components V of t and W t comfortably. This is all about solving a system of equation. Now let us apply these concepts to our problem set 5.1 to solve some of its problems. Question number 1, that is, find the eigenvalues and eigenvectors of a given matrix A with values 1, -1, 2, 4. So as usual, solution, first of all we'll find out the eigenvalues, then we'll find out the eigenvectors. A is equal to 1, -1, 2, 4. And traditional way, first one problem we will do traditionally, rest all problems directly. If it is a 2 plus 2 matrix, directly we can write the characteristic equation. But this problem I will write in a traditional manner. That is, from the diagonal elements we will subtract lambda. We will make its determinant to 0 to get our characteristic equation. What characteristic equation we are getting? This implies 4 minus lambda into 1 minus lambda plus 2 is equal to 0, or that implies lambda square minus 5 lambda plus 6 is equal to 0, but we know, so which implies lambda is equal to 3 comma lambda is equal to 2. How I have solved it? We have a formula that ax square plus bx plus c is equal to 0 implies x is equal to minus b plus or minus b square minus 4ac whole root over by 2a. In this method also you can solve directly if by put the formula, get the answer method. Now for lambda is equal to 3, let us find out the value. So what are the values? Now what is our target? To find out lambda is equal to lambda 1 is equal to 3. For that we are interested to find out the eigenvalues. Eigenvectors, so 1 minus 3 minus 1, 2, 4 minus 3, which is nothing but 2 minus 2 minus 1, 2, 1. It is the matrix. So now this implies, so here ax is equal to lambda ix implies minus 2 minus 1, 2, 1 into x1, x2 is equal to 0, 0. That implies what? That implies, what are the equations then? Minus 2 x1 minus 1 x2 is equal to 0, or x2 is equal to minus 2 x1. What about the vector then? So here this vector x is equal to how much? 1 minus 2. Okay, now this is an eigenvector for, so x is equal to 1 minus 2 is an eigenvector of A for lambda is equal to 3. Now what is our target for lambda is equal to 2? What we will do here, instead of 3 we will subtract here 2. Directly let me write down how much it will be. It is in place of 3 here in this matrix. In place of 3, let us substitute 2. So how much we are getting? -1, -1, 2, 2 into y1, y2, y1, y2 is equal to how much? 0, 0. So what does it indicate? This implies minus y1 minus y2 is equal to 0, or that implies y2 is equal to minus y1. So what about the eigenvector here? The eigenvector y is equal to 1 minus 1. Each an eigenvector of A for lambda is equal to 2. So we got all the eigenvectors required and all the eigenvalues required. So what about the general solution then? The general solution. So here, first part of the question, let us study what it is. First part of the question. Find the eigenvalues and eigenvectors of a matrix A is equal to this much. Verify the trace equal to sum of the eigenvalues and determinant equal to their product. Now what about the trace? The matrix is, what is our matrix? 1 minus 1, 2, 4. So trace is 5, determinant is 6. Okay. Now trace of A is equal to 1 plus 4, that is 5, which is equal to 2 plus 3, that is equal to lambda 3 plus 2. Okay. Okay, lambda 2 plus lambda 1. Okay. So what we got? Sum of the eigenvalues of A is equal to trace of the matrix. So therefore, sum of eigenvalues of A is equal to trace of A. This is being obtained. Similarly, what about determinant? Determinant of A is nothing but 1 minus 1, 2, 4 determinant. So 4 plus 2, that is 6, which is equal to 2 into 3, that is lambda 2 into lambda 1. So product of eigenvalues of A is equal to determinant of A. This also clearly indicates. So next question is, what about next question? Let us study question number 2. What it is telling us? With this matrix A and U is equal to 0, 6, we are expected to solve the system of equation. What are the two pure exponential solutions? So here we are expected to find out V and W, which will be always in the form of exponential. So what it is? Question number 2. So this equation is du by dt is equal to au, u of 0 is equal to 0, 6, and here a is equal to same as question number 1, that is 2, 4. That implies lambda 1 or lambda lambda 1 is equal to 3, lambda 2 is equal to 2, and the corresponding vectors x1 is equal to 1 minus 2, and the corresponding vector x2 is equal to 1 minus 1. Already these things are there in the question number 1. So from this, we have to create some space, otherwise it will create some problem also. So what it is telling? So I have eigenvalues and eigenvectors. So what about the general solution? The general solution of 1 is how much? U of t is equal to C1 e to the power 3t 1 minus 2 plus C2 e to the power 2t 1 minus 1. Now substituting t is equal to 0 for t is equal to 0, u of 0 is equal to 0, 6, that is equal to how much? Here t is equal to 0 means this exponential terms will become 1, so it is C1 plus C2 and minus 2C1 minus C2. So from here what we got? This implies C1 plus C2 is equal to 0, minus 2C1 minus C2 is equal to 6. So adding these two, we are getting minus C1 is equal to 6. So C1 is equal to minus 6. We got it. So what about C1 then? In that case, C1 is equal to plus 6. So, it is going to, sorry, C1 is equal to minus 6. What is it? C2 C1, how much we got? So this C2 into this much. So when I substituted, what I got? C1 plus C2 is equal to 0. Then here minus 2C1 minus C2 is equal to 6. C1 plus C2. Whatever it is, this I feel it is, if not wrong, it is correct only. Okay, so here we got C1 is equal to minus 6. This implies C1 is equal to minus 6. So that implies C2 is equal to 6. This is minus 6 and C2 is equal to 6. So what about the solution? The solution to the IVP is u of t is equal to minus 6 times e to the power 3t 1 minus 2 plus 6 times e to the power 2t 1 minus 1. There is no confusion at all. So from here, this is nothing but v of t, w of t. So the exponential form of the solutions are what? B of t is equal to minus 6 e to the power 3t plus 6 e to the power 2t, and W of t is equal to plus 12 e to the power 3t minus 6 e to the power 2t are the exponential form of the solution. Solutions form of solutions. So we are obtained. They are the two pure exponential form. They are the here two pure exponential form of the solutions. Hence it is understood. Now next part of the question is question number 3. Here directly we will do it. We will apply the properties. Here what about question number 3 is telling? A minus 7i. What are the eigenvalues and eigenvectors of which are related to those of A minus 7i? We know here one of the significant property. So that property was missing there in the list. Okay. So here it is, I will write this color. So what it is? Question number 3. A minus 7i has eigenvalue lambda minus 7, values lambda I minus 7, and eigenvectors xi. Therefore A minus 7i, what about its value? Its value is, how much it is written, just let us verify the question. Okay, minus 6 minus 1, 2 minus 3. Minus 6 minus 7, 2 minus 3 has eigenvalues A माने कहते lambda I कहते 3 minus 7. So 3 minus 7, that is minus 4, and 2 minus 7, that is minus 5, and the corresponding eigenvectors are same. The corresponding eigenvectors are for lambda is equal to minus 4, lambda is equal to minus 4 is 1 minus 2, 1 minus 2, and for lambda is equal to minus 5 are scalar multiple of 1 minus 1. So this is the question number 1. Now question number 8 we will do what it is telling. So that determinant equals to product of the eigenvalues of a given matrix. Sorry for the inconvenience. Let me stop the video here.